Okay, welcome to Chapter 7. In Chapter 7, we're looking at multiplying vectors. So we haven't looked at that so far. So far we've added, subtracted, and we've multiplied a vector by a scalar. But this time we're going to multiply two vectors together. And there's two ways to do that. The first is called dot product, and it uses the symbol a dot. And the second one is cross product, and it uses the symbol a cross. So that'll help keep them straight. That means that when I multiply two vectors, I can never just write A, B with no symbol in between. You have to tell me what kind of multiplication are you doing. Are you doing the dot product of the vectors, or are you doing the cross product? At the end of the chapter, we're going to look at some applications of these two different operations, things like work, torque, and the area of geometric shapes. And so again, this is not okay anymore. All right, so in today's first lesson, we're looking at the dot product of geometric vectors. So geometric ones are the ones that are not glued to the Cartesian plane. They're kind of just floating around with some angles in between them. So we're starting off with two vectors, vector u and vector v, and the dot product between them is u dot v, and that's going to be equal to the magnitude of vector u times the magnitude of vector v times the cosine of the angle in between them. So again, theta is the angle between the two tails of u and v. One of the things you want to notice here is that the dot product answer is a scalar, not a vector. And so that's interesting. When we look at cross product later, you're going to see it's the opposite is true. The answer is a vector. So how can I tell when I look at this formula that the answer, this thing that I'm calculating, is scalar? Well, here I've got a magnitude, that's a scalar, times a magnitude, that's a scalar, times the cosine of an angle, which is also a scalar. So altogether, scalar. All right, so we're going to talk about, well, how can I tell what kind of an answer am I going to get? And it depends on that angle in between the two vectors. So again, I'm talking about the angle between the tails. So if I have an angle that's somewhere between 0 and 90 degrees, so I have an acute angle, is what's happening there, then I can think about, well, what is the cosine of that angle going to be? So I'm just kind of thinking through this formula. If I know that this is an acute angle, then the cosine of an acute angle is greater than 0. I can be thinking about like the cast rule, right? If the angle is between 0 and 90, then I'm in this quadrant here, and all the ratios are positive, so cosine is positive. And so then that tells me that I'm going to have a positive number here at the end times a magnitude times a magnitude. And magnitudes are lengths, so they are positive as well. So this answer is going to be a positive answer overall. Okay, so next up we're going to take a look at what happens if theta is actually equal to 90. So you might remember that if I'm actually right here on this axis, the cosine here is equal to 0. If you can't remember that, you could check on your calculator. Whoops. So cosine of theta is equal to 0, and then I can imagine, again, plugging that into my formula here for the dot product. Cos theta would be 0 times the magnitudes is going to be equal to 0, no matter what the magnitudes are. So this is kind of an interesting case. I'm going to come back to this one. And in our last case, if theta, the angle, is between 90 and 180, right? So like our vectors kind of look like this, and the angle is an obtuse angle, then if I was thinking about the cast rule, I'd be in this quadrant over here, the S quadrant, in which case the cosine of the angle is going to be a negative answer. So now I'm going to have a negative number times the two positive lengths, and overall that's going to give me a negative dot product answer. So I should be able to tell if I'm going to have a positive, negative, or 0 answer just by taking a look at that angle. So just a note about this one here, this is a really useful property that the dot product is equal to 0 when the angle is equal to 90 between the two vectors. So imagine those two vectors then must look like this. And that can be rotated, right? Like vector v could be pointing down or to the left, but then vector u would still have to be a 90-degree angle between them. So whenever I have these perpendicular vectors, I'm going to have a dot product of equal to 0. So we'll look for this word in our questions, perpendicular or 90-degree angle, and that's going to remind me that I can use this useful property that the dot product equals 0. All right, in our first example, just straight up, just plugging into the formula, calculate the dot product of vector A and vector B if the magnitude of vector A is 20 and the magnitude of vector B is 30, and the angle in between them, remember that's between the tails, is 40 degrees. And remember in the formula, the theta is also the angle in between the tails. So they've given me the correct angle. I just need to plug this in. So I'll say that the dot product of vector A and vector B is equal to the magnitudes multiplied times the cosine of the angle in between them. And then we'll fill in what we know. So 20 times 30 times cosine of 40 degrees. And again, my calculator is in degree mode, and I'm going to round this to the nearest decimal, or to the nearest one decimal place, sorry. So about 459.6. I don't have any units for the dot product. That'll come in some of our applications. All right, so properties. This is like the rules. What can I do with dot products? What kind of algebra is allowed? So in the first one, it's our associative property. If I have some scalar multiple k times vector p, so I would figure out what that is, and then dot it with vector q. That's actually the same as, this is telling me, the brackets say, take the dot product of p q first, and then multiply by the scalar k. Or over here, if take the vector p and dot it with, first find the answer to k times vector q. So this is kind of saying, like, no matter which thing you do first, I would have to do the thing in brackets first, I'm going to get the same answer. So here k is a scalar, and I can move it around the dot product and it's not changing my answer. That's what's important here. Okay, the next property is the commutative property, and that just tells me that the order of the dot product doesn't matter. And you can imagine that in the formula, if I were doing v dot u up here, if I changed the order, the only thing that would change is the order that I multiply the magnitudes in, right? The angle between them is still going to be theta. And so, of course, this is going to give me the same answer. And then there's the magnitudes property. If I take the dot product of a vector with itself, again, just remembering the formula, p dotted with itself, that would give me p, the magnitude of p times the magnitude of p times the angle between. Now, if it's a vector dotted with itself, p and p on top of itself, the angle between them is actually just 0. So this would be the cosine of 0 here, or you could think of it as 360 degrees. And the cosine of 0 is just equal to 1. So then I would just be left with the magnitudes times 1 at the end, which is the same as the magnitude squared. So that's where that comes from. And then the last property, this one's pretty useful for us. If I have a vector addition in brackets, so I would figure out what that resultant vector was, and then dot it with vector p, that's the same as dotting vector p with both of the original vectors q and r, and then adding that result. So that's kind of interesting. This is the distributive, right? It's kind of like, I'm just like the distributive property in algebra. I'm just distributing this through to come up with PQ times P plus PR. All right, example 2 here, we're going to take these two vectors, 2a minus b, and we're going to be looking at this other vector, a plus 3b. And I know that these two vectors are perpendicular. Now notice that these two vectors are some resultant, right? I'm stretching out vector A twice as long and then tacking on to the head the subtraction of vector B, and then finding that resultant vector. So these two resultant vectors are perpendicular. I know that the magnitude of A is equal to the magnitude of B, so they started off the same length. I want to determine the angle between the original vectors A and B. So the problem that most students have with this question is that there's two angles and they kind of get them confused. So there is an angle between the resultant vectors, these two here. It's 90 degrees. I know that they're perpendicular. But what I'm trying to find is the angle between the original. So I'm just going to go for a quick second to explain to you that these are two separate angles. So if I'm starting with vectors A and B over here, there's some angle between them. I just chose a random angle to draw these at. Then I can come up with the first resultant vector that they're actually talking about in the question by taking two A's and subtracting B. So I switched the direction there. And so this is the first vector that they're giving me. And then the second vector was A plus 3B. So again, I took an A from over here and I tacked on 3 B's and I find that resultant vector. Now what I know is that the angle between these two resultant vectors is 90 degrees. So obviously I've not chosen the correct angle over here, but I want you to convince yourself that this angle in here is not the same as theta. So I can do that if I take this image over here and just kind of drag it on top. I can rotate it, and you can see here that these guys are not the same angle in between them. So just keeping in mind here that there are two different angles. We know that this one is 90. We need to go back and figure out what the original was. All right, so let's do that. We're going to start with the fact that I know that the vectors are perpendicular. I warned you earlier in the lesson this was going to come up. If I know that two vectors are perpendicular, I know that their dot product is equal to 0. So 2a minus b dotted with a plus 3b must be equal to 0. And so we're going to try to simplify this so that we can come up with the angle between the two vectors. Now, if I want the angle between these two vectors, then I'm thinking, well, it'd be nice to know a dot b, because then I would know, I would have a formula, that involves the angle between them. This is the angle that I'm looking for. All right, so let's see if we can come up with this piece inside this equation so that we can come out with a theta. Remember before that we said that the distributive property works here between the dot product and addition subtraction. So that's what I'm going to do here. I'm going to multiply 2a times this second bracket. And so I'm going to get 2a dotted with a. Remember, the dot is important here when I'm multiplying vectors. You have to tell me what kind of multiplication. And then I'm going to have 2a dotted with 3b. Remember, our properties from above tell me that I can move the scalar around. So I can bring the 2 and the 3 together to the front and say that that's the same as 6, and then a dot b. And then I can do the same thing now. I can take the negative b and multiply it through the second bracket. So negative b times vector a. So again, the coefficient to the front, negative 1. And then I've got b times a, or b dot a. And then we'll do the same thing over here. The coefficients are negative 1 and positive 3. I can bring them both to the front and multiply them together. And then I get b dot b. All right, so now we're going to try and clean this up. I see some of this happening, which is what I wanted. That was my goal. And so what I can do here, I know that one of the things I can switch is that b dot a, the order doesn't matter. So this is the same as a dot b. So that's going to be nice for me, because now it's almost like kind of like having like terms here. I've got 6 a dot b's and minus 1 a dot b. That's going to be 5 a dot b's. And then tagging along here, so we said these middle two, I can kind of collect them. And then I can also change the a dot a's, but I'm going to do that all in the same step here. So at this point, I've got all these dot products and I know that I'm interested in the angle in between. So what I'm going to do is switch all of these over to the magnitude form instead of dot product. Now remember, when I'm dotting a vector with itself, we know that that dot product is equal to the magnitude squared because the cosine of the angle is 1, so that kind of goes away. And then in the middle here, and then same thing at the end, b dot v is just the magnitude of vector b squared. Okay, so we're getting closer. Remember our goal, you always want to keep your eye on the goal here. The goal is to figure out what this theta is equal to. So what I'm going to do here, I'm going to use the other piece of information they gave me up in the question. I know that magnitude A is the same as magnitude B. So I'm going to substitute that in to kind of get rid of some of these things. I'm going to sub it in the other order, but it does not really matter. I'm going to end up with all A's, but if you subbed it in the other order, you'd have all B's. So, oops. So I'm replacing all my magnitude B's with magnitude A's. And some variations on this question, instead of telling you that the two magnitudes are equal, they might actually give you values for those magnitudes. And then at this stage, I would also just substitute in those numbers for the magnitudes. That would work as well. So now what I see again is I've got some like terms. I've got 2 times the magnitude of a squared minus 3. So that's negative 1 times the magnitude of a squared. And then here I can clean up this. This is 5 times the magnitude of a squared times cos theta. We're getting there. I want to solve for theta, so I'm going to rearrange this equation. So I'm trying to get the theta by itself. So first, it's kind of like just reverse BEDMAS, right? I'm moving things away from that, and I start with adding and subtracting. So I'm going to take the negative magnitude of a squared over to the other side and add it. And then I'm going to divide out the coefficient in front of cos theta. So we've got this whole coefficient here. I'll divide it over to the other side. Okay. I know that I can divide this out, even I'm dividing by a variable here. I know that I can because in the question they told me that A was a non-zero vector. So I know that the magnitude of A is not 0. All right, so now I can do a bit of canceling. I've got the magnitude of A squared as a common factor, top and bottom. And there we go, nice and simple. Now we just have to take the inverse of 1 divided by 5. And so again, I'm just typing that into my calculator, and I get about 78.5 degrees between the vectors A and B. All right, have fun with that homework.